First objective, to model the rule-based standalone system. Second objective, to obtain the optimal sizing for the system in order to minimize the cost of energy at specific losses of power supply by using particle swarm optimization algorithm. Lastly, to make comparison between particle swarm optimization method and the iterative method. The scopes of this project, integration between PV and thermoelectric generation with battery bank in order to configure the standalone system. The temperature, radiance, and load profile has used as the input data. Also, the heat sink and control system is not considered in this work. The ambient temperature used as the cold side temperature of the thermoelectric generation. MATLAB software has used to analyze this system. This table describes some related work. For example, reference 9 using PV and battery bank as the source in order to minimize power losses supply and cost of energy by using iterative method. Another method using hybrid system as the source in order to minimize cost of energy and minimize the efficiency of power supply by using artificial method. This flowchart describes the research methodology of this work. First, obtaining the climate data, structure the components, modeling all components of the system, simulate the energy management system, calculate the losses power supply and cost of energy, lastly, sizing the system. To get the optimal sizing of the system, first step, obtaining the input data, which is load profile, solar radiance, temperature. Second step, modeling each standalone system components, modeling PV system by using this equation, modeling thermoelectric generation array by using this equation. Lastly, modeling battery storage system. This slide shows the input data for the target location, which include temperature and radiance with the load profile. The daily energy requirement is almost same every day during 1 year. For 1 day, as shown in this diagram, about the peak load about 96%, and the base load demand around 10 kilowatt. This slide shows the block diagram of all the components of the standalone system: PV array, thermoelectric generation array, converters, battery storage system, and AC load with dump load. Power flow management in this work using rule-based algorithm in order to achieve the first objective. There are 4 main operating mode. First operating mode, if the power from source more than demand and the state of charge less than maximum value. In this case, the storage will charge. The storage system will charge. Second operating mode, if the power from supply more than demand and state of charge more than maximum value. In this case, the dump load will be operated. Third operating mode, if the power from supply less than demand and the state of charge more than minimum value. In this case, the storage system will discharge. Lastly, if the power from supply less than demand load and state of charge less than minimum value. In this case, there is a losses of power. First objective function in this work, losses power supply. Losses of power supply is the ratio between the energy shortage and demand of the demand for the long time. Also, it uses to describe the reliability of the system to supply load. The desired losses power supply value is selected 1% in this work. This flow chart describes how exact to determine losses power supply. If the demand more than energy that produced from source and the energy that exists in the battery bank, in this condition, losses power will determine. This situation will repeat it for a year. After completed the iteration, losses power supply will determine by using last equation. Second objective function of this work, cost of energy. Cost of energy, it is the constant cost of energy per unit. Cost of energy is the ratio between total net percentage cost and the total load per year. Total net percentage cost, this work included all installed capital cost, replacement cost, operating cost, and maintenance cost. CRF is the capital recovery factor. The proposed sizing method in this work, which is particle swarm optimization. Another method has used, which is a iterative method, in order to make comparison with the proposed method. First, we start sizing the system by using iterative method. This method depends on the iteration. Iteration when the best configuration is obtained. This method has some disadvantages, such as it requires a large number of iterations. It requires a lot of calculation and time to obtain the best design. This flow chart describes the iterative method and how it was modeled in MATLAB. We start with one battery and one panel, then increase the number of the panel to the maximum number. After that, increase the number of battery until it reaches the maximum number. In each case, if the losses power supply less or equal to the desired losses power supply, the configuration will be stored in the cost. Will be stored. Also, the cost of energy is will calculated. In the end, we will have many possible configuration. The most optimal configuration is the cheapest one. Particle swarm optimization algorithm is the proposed method in this work. There are four main steps how to model this method: initialization, updating the individual and the global visit, updating the facility position, check the feasibility. This flow chart describes particle swarm optimization, how it works and how it modeling in MATLAB. As I mentioned, four main steps. After initialization parameter, calculate the losses power supply and cost of energy. After that, updating the individual and the global visit, updating the velocity and the position. Lastly, get the optimal sizing from the global visit. This is slide as the result. This slide describes the losses power supply analysis and the relationship between losses power supply and cost of energy. The figure on the right side shows the losses power supply analysis. It shows the simulation of the result for 50,000 configuration with different number of panel and batteries. As we see, the dark blue region has a low losses power supply, meaning that high system reliability. The yellow region has high level of losses power supply, meaning that low level of system reliability. Since the battery bank is energy storage, so it does not generate any energy. Increasing the number of the battery bank does not reduce the losses power supply if the panel not enough. Besides that, the figure in the right side describes the opposite relationship between losses power supply and cost of energy. The figure on the right side describes the opposite relationship between losses power supply and cost of energy. Configuration with low volume of losses power supply has high cost. In contrast, configuration with high losses power supply volume has low cost. This slide shows the simulation result of the iterative method. By using the iterative method, 33 possible configuration with 1% losses power supply have obtained. Each configuration has different cost of energy, as we see in the diagram. The most optimal configuration is the cheapest one, as we see in the red line. Each configuration has different number of components. The most optimal sizing of the system has 419 panel and 47 battery with a minimum cost with about 0.58 ringgit per kilowatt hour. In contrast, this slide shows the simulation result of the proposed method, which is particle swarm optimization. By using the particle swarm optimization, one configuration with 1% losses power has obtained, which is optimal sizing of the system, as shown in this figure. Particle swarms optimization start searching for the best design from random configuration. After that, be searching and repeating until reach the best design, as we see in the iteration number 25. The most optimal sizing of the system, as shown in this table, around cost 0.5812. As the result, by using two methods, we can see, say particle swarm optimization is very fast. We got the best result less than 100 iteration. Also, it reduced computing time, consumption of computer resources, and able to get best result compared to the iterative method. The iterative method require a long simulation time since all the system configuration needed to analysis. Although the iterative method has some disadvantages, but it also almost get the best design. After obtaining the best design, the energy flow can be analyzed by using a rule-based algorithm. In this slide, as we see in this figure, contribution of the energy produced by a panel during 1 year, PV contributed about 86%, and thermoelectric generation contributed about 14%. Also, we can see in this the figure the contribution of the power data flow to the load during 1 year. This figure shows the data collected from the system simulation using 450 panel during 1 year. Yellow line describes the thermoelectric generation power. Red line describes the PV power. In this figure, blue line shows the generated power. Red line shows the power demand. Yellow line shows the describe and charge. This for the yellow line shows the discharge and charge for the battery bank. About the state of charge is set between 13% to 19% in order to increase the lifespan of the battery bank. So assume the battery bank is depleted if the level reach 30%. In contrast, the battery bank is fully charged if the level reached 19%. As conclusion, this work focuses on design the optimal sizing. The system used meet the energy demand for the target building at 1% losses power supply probability and minimum cost. As the result, BSO able to achieve the best design. The best system configuration included 415 panels, each rated 420 watt, with 48 battery bank, each rated 9.6 kilowatt. PV contributed about 71 of the demand. Thermoelectric generation meet about 12% of demand, and battery bank around 17%. In the end, I will thank you for your attention.
Okay, thank you, Munir, for your presentation. And now I'm open to the floor for any questions. Any question? Okay, Munir, how you set the parameters of the PSO?
Yes. For the parameter for the weightage, I choose one. For the weightage for PSO 1 and C1, C2, C1.75, C2 1.75 for the all power.
You did any experiment if you change the parameters?
No. This is out of scope. Just this paper comparison between iterative method and the particle swarm optimization. Basic BSO.
Oh.
Just choose one value of parameter, all parameter, or BSO parameter.
Okay, how you want to confirm is a good result based on your parameter that you have choose?
Yes, for the result, because the iterative method almost consider the accurate method because all configuration we have to simulate. It needs a lot of time, so that we made the comparison between BSO and iterative method to confirm the result for the BSO.
So you not optimize the PSO itself. Maybe later you can do some
Yes, good idea for that. Change the parameters
to see the improvement might be for the PSO application to this PV and TEG system might be.
Yes, good idea for this. Because we will change the BSO parameter, the result will be changed.
Okay, you just compare with the iteration technique. Okay,
yes.
The BSO and the iteration technique.
This is
of BSO itself, you can do the in terms of the changing the parameters, and then we see the performance of the BSO itself.
Yes.
Okay. Is there any question from the floor? Okay, seems no more questions. Okay, in that, thank you, Munir, for your presentation. Okay, then, all right. Before that, I want to remind to all of you, please stay in this session, because at the end of this session, we will have a photo session. Okay. And then I invite the next presenter, Abiadun, right?
Yes.
Abiadun, he will present on the data-driven model for human tracking and prediction using Kalman filter with PSO. Okay. Abiadun, you can share your slide.
Okay,
then
sir.
Proceed to the presentation when you're ready.
Assalamu alaikum.
Can you put in the slideshow?
Okay, sir. Is it okay like this?
Yeah, you can see.